So the number I got was number 17, which was cyclohexyl 2-cyclohexoxypropanoate. So I was given the diagram, and in order to name it, the first thing I did was to locate a functional group, and the first one I saw was on the first main carbon, which was an ester, as there is a carbon double bonded to an oxygen bonded to another oxygen. So this automatically told me there would be an ending of OATE. I also noticed that there's a chain of 3 carbons, so it would be a root of propan. So from here, I identified another functional group on the second carbon, which is an ether, oxygen bonded to 2 R groups. And in this case, it's bonded to a cyclohexyl group, and it would give it the ending of cyclohexoxy. So on the second carbon, it would be cyclohexoxypropanoate. And lastly, there's a cyclohexyl branch connected to the ester. So it'd be cyclohexyl 2-cyclohexoxypropanoate. The condensed structure is right here, and the line structure is right here. So moving on, I'm gonna move on to the properties. So first I'm gonna talk about the reactivity. So ethers have low boiling points since there's no hydrogen bonding other than the hydrogen bonding between water and alcohol. Ethers are also used as solvents and are known to be least reactive common class of organic compounds. So they're low reactivity. The cyclohexyl groups are very stable, are nonpolar and low reactivity. The esters are, however, the esters are reactive since they have polar bonds between oxygen and carbon, which make it reactive. So overall, it would be low reactivity. For the molecular geometry, for the ester, there is a carbon bonded to an O, bonded to a CH, double bonded to an O, and it is a trigonal planar with a bond angle of 120 degrees. For the ether, there is an oxygen bonded to a cyclohexyl group, bonded to a CH, and the oxygen has lone pairs which push these two together, which give it a bond angle of 104.5 degrees and give it a molecular geometry of bent/angular. The cycloalkane, which is a cyclohexyl, would have a tetrahedral shape and have a bond angle of 109.5 degrees. So for moving on to polarity, the polarity is determined by polar bonds, which are then determined by the difference of electronegativity. So if the difference of electronegativity is greater than 0.4, it is a polar bond, and if it is less than 0.4, is a nonpolar bond. So in this case, the carbon and hydrogen electronegativity difference would be 0.4, so it'd be slightly nonpolar, and the carbon and oxygen electronegativity difference would be 1, so it'd be polar, so it would be a polar molecule as there are more carbon and oxygen bonds. However, the cyclohexyl and these nonpolar bonds bring it down, so it'd be slightly polar. Moving on to solubility, both ethers and esters are soluble. So esters can form hydrogen bonds through oxygen atoms to the hydrogens of water, which make them slightly soluble. And ethers decrease solubility with more carbon atoms. So being bonded to a cyclohexyl, the solubility will decrease, so which will make it slightly soluble. And lastly, the intermolecular forces. So esters and ethers both are polar molecules and have dipole-dipole interaction and London dispersion, as every molecule will have even the weakest bit of London dispersion. So the ether is bonded to carbon and oxygen, which is a polar bond, and it will have dipole-dipole, slightly negatively charged and positively charged ends. Moving on to the second part of my molecule the second molecule I got was trans 2-amino 3-methyl oct 4-ene-2-ol. So I was given the name and was told to draw the structure. So the first thing I seen was the ending, the root. I got oct 4-ene. So this told me that there will be 8 carbons and a double bond on the fourth, as there's an ene and a 4. So I drew 8 carbons and a double bond. And it also told me on the second carbon there's a OL, a hydroxyl, a alcohol group. So I drew a OH. It also tells me there's a 2-amino, so on the same carbon there is a NH2 group. So I drew an NH2 group here. And on the third carbon, there's a methyl group. So I drew a methyl group right here. Over here it says trans. So this tells me that it's the hydrogens should be on opposite sides instead of the same sides. So I drew one hydrogen here and one hydrogen there. So this is the expanded structure I got. Here is the condensed formula. And here is the line structure. And moving on to the properties now. So the reactivity, so this is an amine. So the amines are very reactive as they're basic. They react with alkyl halides, acid chlorides, and carbonyl compounds. There's also alcohol group. They're reactive as there's hydrogen bonding, OH bonding, and there's a higher boiling point than alkanes. So the alkene over there they're relatively stable and aren't that reactive. For the molecular geometry, so the amine group here is a nitrogen bonded to a carbon and two hydrogens, and is a trigonal pyramidal and has a bond angle of less than 109.5 degrees. The hydroxyl group has an oxygen bonded to a carbon and a hydrogen. The lone pairs push these two away closer to each other, push them closer to each other, and give it a bond angle of greater than 109.5. And it is bent / angular molecular geometry. The alkene is a trigonal planar and has 120 degrees bond angle. So moving on to the polarity. So as I said before, the electronegativity determines the polar bonds. So the polar bond between carbon and oxygen is 1.1, so this is polar. Carbon and nitrogen is also polar, it's greater than 0.4. Carbon and hydrogen is nonpolar, and nitrogen, hydrogen is polar, and OH is polar. However, there is a lot more CH bonds, so this would be a non-polar molecule since there is a lot more CH bonds. Moving on to solubility. So small amines are very soluble in water, and amines and both hydroxyls can form hydrogen bonds in water and therefore are both soluble. However, due to the large alkyl groups, the solubility decreases. And lastly, the intermolecular forces. So for amines, it is a polar molecule and experiences dipole-dipole and London dispersion, as every molecule experiences that force. And also has hydrogen bonding between N and H. And the hydroxyl also is polar and has London dispersion and also has hydrogen bonding between hydrogen and oxygen. So that's all for my molecule assignment.